Okay, the next thing to do with work and energy that we want to look at is whenever energy isn't conserved. Rather, there's a force putting energy into the system or a force being taken out or energy being taken out of the system, for example, by resistances. And it's quite straightforward in that the change in energy will simply be the work that's been done by the force, whether that's energy put into the system or energy taken out of the system. Or quite nicely, it can be written like this. The initial kinetic energy plus the initial potential energy plus any work done put into the system will equal the final kinetic energy plus the final potential energy plus any work taken out of the system. Your work going into the system can be a push or a force or maybe a driving force or an engine. Work going out is going to be work done against friction or resistive forces that take energy out of the system. But one thing that we don't include is we don't include gravity in that work done against friction or work done against gravity, because that's part of your potential energy or the change in potential energy. So we really only look at resistive forces. So we have an example here. A constant force pushes a mass of 4 kilograms in a straight line across a smooth horizontal surface. It's important that it's smooth because there's not going to be any friction then. And so there's not going to be any work out against that friction. The body passes point A at 5 meters per second and point B with speed 8 meters per second. AB is 6 meters. Find the magnitude of the force acting on the mass. Okay. So very simply, it's a straight line. It's going across from point A to point B. It's a smooth horizontal surface, and here it's going at 5 meters per second, and when it gets to here it's going at 8 meters per second. So we can say that the initial kinetic energy plus the initial potential energy plus any work that goes in will equal the final kinetic energy plus the final potential energy plus any work that goes out. And again, we've seen that there's no resistances here, there's no friction, so that work out is going to be 0. And actually, it's all on the same level here. I guess we should check. It says horizontal surface, so it's all the same level. And so the potential energy, there's no gain or loss in potential energy, so we can put zeros in for all the potential energies as well. Now the kinetic energy at the start is a half times the mass times its velocity squared, so 5 squared. And the work going in will be any force that pushes it. So we have a constant force, let's call that F. And it's pushing it for the entire distance here of 6 meters. So the work that will go in from that force will be F times S, which is 6 times that force F. And that's going to equal to the kinetic energy at the end, which is a half times the mass times the velocity squared, 8 squared. So when we work through this, this is 50 plus 6F equals 64 times 2, 128. So 6F is 78 and the force F is 13 newtons. Just put that up here. Force is 13 newtons. A second example then. A block of mass 5 kilograms projected with velocity of 5.6 up a line of greatest slope of a rough inclined plane. So we have a lot going on here in this one. If we just do a very quick sketch. Then this angle is theta here. We have the thing going up the slope. The normal reaction, and its weight is going to be 5g. And it's going from, say, this point here, the initial point, up to this final point here. So I'm going to pick this, the bottom of my slope for the potential energy to be 0 at that point. And we need to find out then what's this vertical distance, what's this height h. Now we are told in the question sine theta is 3/5. So sine theta is 3/5. Then doing a quick wee diagram, might not even need it. The opposite is 3, hypotenuse is 5, so this is 4 by Pythagoras' theorem, and I know quickly that cos theta then is 4/5. And we'll need that later on because we know that this little angle in here is theta. We're going to have to resolve that to find out what the normal reaction is. Now, the other thing we know that this distance all the way up and down is 5.6 meters. Now, what do I know to start with? Well, I'm just going to write down here the kinetic energy initially is a half times the mass times the velocity squared, so 5.6 squared, which ends up as 78.4 joules. The potential energy initially, well, we've said it's down the bottom here. I'm going to say it's 0. Now, the work in, well, there's no work put in this. We're not told that there's a constant force pushing it up. We're just told that it's projected up. So there's no forces acting on that to put energy into the system. On the other hand, when we look at it, finally, once it gets to F, it comes to a stop there. It comes to a rest. So its velocity is 0 and its final kinetic energy there is 0. Its potential energy, though, is going to be the mass, which is 5, times 9.8, times this height h here. Now, if that's theta and this is 5.6 meters, then I want to find h here, and that's h is equal to 5.6 sine theta. Now, sine theta is 3/5. Sorry, that's not 5.6, it's 2 meters up the slope. 2 meters, sorry. That's 2 sine theta, which is 3/5 times 2, or 6/5, or 1.2. Okay, so we put 1.2 in there. And so the final potential energy there is 58.8 joules. Now, we will have work going out, and that work is work done against friction and coefficient of friction. So we need to find that. But I know that work will be F times S, the force times this distance, which is nice and easy, it's 2. And the frictional force would be maximum value of friction, so it's going to be 2 times mu r. Now, to find r, we need to resolve perpendicular to the slope, and that's going to be, r is going to equal 5g cos theta. So that's 2 times mu times 5g cos theta. And I know what cos theta is. We've worked it out up here as 4/5. So that's 2 mu times 5g times 4/5. And that works out as 78.4 mu. Okay, again, taking g to be 9.8 here. In maths, you always take it to be 9.8 unless you're told otherwise. Now, going back to our work energy equivalence, this initial kinetic energy plus the initial potential energy plus the work in equals the final kinetic energy plus the final potential energy plus any work out, or any. So what do we get? We get 78.4 plus 0 is equal to 0 plus 58.8 plus 78.4 mu. Rearranging that, we get 78.4 mu is 19.6, and so we find mu to be 0.25. So the work done against friction is going to be 78.4 mu, and mu is 0.25. And so I guess we could actually find that the work done against friction is 78.4 times a quarter 78.4, which is 19.6.